Single-agent models perform reliably in isolated conference demos. However, these same models frequently fail when deployed into sustained, multi-day production environments. The dominant architecture of 2024 relied on a tightly supervised hierarchy. In this model, a central planner decomposes a goal and delegates it to specialists. This supervised approach hits a bottleneck once the system attempts to manage more than a few dozen concurrent specialists or encounters dense, dynamic interdependencies. These bottlenecks manifest as unmanageable token traffic costs and the eventual collapse of the global state. Current production systems are moving toward a swarm-aware paradigm. These models replace central planners with decentralized concurrent agents that coordinate through local logic. Scaling this shift requires three architectural layers: swarm-aware topologies for routing, the OCS protocol for meta-orchestration, and KickLang for cognitive transport. Increasing raw compute or model size on a failing topology only accelerates hallucination cascades. Achieving production scale requires rebuilding the underlying structural protocol. A swarm-aware agent carries its own routing logic, handoff policies, and local failure strategies. It operates as a self-contained unit within the collective. Loose, pure swarm routing works for independent parallel synthesis. High-stakes workflows, however, require a designated quorum threshold. A hybrid topology merges these modes into a single runtime. Here, adaptive quorums dynamically negotiate decision thresholds based on risk and agent integrity. Purely digital swarms remain vulnerable to gradual semantic drift. Over long execution runs, this lack of physical context leads to hallucination cascades. To prevent this drift, swarms anchor themselves to physical hardware nodes. Berlin-class servers report real-time execution states and hardware pressure to provide a shared reference body for the collective. Hybrid topologies manage the concurrency of the agents, while these external hardware anchors maintain the coherence of the data. Without a governing meta layer, decentralized swarms become opaque and unpredictable under significant load. The Orion Collective System, or OCS, provides this governance. It is a strict enforcement protocol that sits above the individual agent frameworks to define the contracts every participant must honor. OCS enforces consent-first execution. High-impact actions, like external API calls, are blocked until a human or high-integrity agent issues a specific cryptographic token. This consent requirement acts as a hard gate in the state machine, providing essential security for production environments. OCS also implements failure algebra. Instead of a total system restart, agents publish typed failure modes like timeouts. The system reads these failure types and dynamically recomposes a new routing path around the problematic node while preserving global state. To prevent unbounded recursion, the protocol enforces meta-iteration limits. This places a hard ceiling on self-modifying loops, ensuring the swarm reaches a conclusion. OCS utilizes the three-agent core, extraction, synthesis, and review, as its canonical pattern. This triad serves as the minimal recursive building block for larger collectives. The protocol does not dictate the internal reasoning of the agents. It provides the contractual governance required to make the swarm auditable and safe. Moving knowledge between agents is a technical challenge. Natural language prompts are too lossy for cross-node reuse, while raw code is too difficult for humans to inspect quickly. KickLang is the standardized transport language designed for this purpose. It is a formal, bidirectional medium that serves as the contract for moving cognitive modules. Modules declare typed input channels, internal transformation logic, and emitted outputs. These modules carry cryptographic provenance. Every block includes a unique build ID and a hash of its source intent, allowing the system to track the lineage of any piece of data. This strict schema enables live migration of running graphs. A swarm can pause execution on one node and resume it on another, even across different organizations, with no loss of fidelity. Thus, KickLang is readable by design. A human engineer can inspect any module mid-flight to understand its intent and refine its guard conditions natively. KickLang turns cognitive work into shippable, inspectable software packages, making humans first-class participants inside the execution loop. These three layers create a closed loop. Swarm topologies provide concurrency, OCS ensures governance, and KickLang packages the knowledge. This loop allows partial results to travel safely across nodes, enabling the collective to improve its output over long, complex runs. For engineering teams, the optimal build order reverses expectations. Success starts with clear KickLang module contracts, followed by the OCS governance plane, and finally, autonomous swarms. Building large swarms before establishing transport and governance protocols leads to system failure under real-world load. These protocols also provide the technical foundation for cross-organization federation, turning the problem of sharing agent workloads into a solvable contractual question. The success of future multi-agent systems depends on the rigor of the contracts binding grounded nodes, specialized agents, and human participants together.